All right, so let's continue where we left off in numerical integration. We talked about the composite rules, and we saw how useful and more interesting they are than just looking at just a simple rule over just the entire interval, right? So the composite rules are used to break up an interval into smaller pieces, right? And then we can use our simpler rules to be able to get a pretty good approximation. We saw that the trapezoid rule gave a pretty good approximation in that last example when we integrated from 0 to 2 for x cubed. The left endpoint didn't, but that's okay. And then, of course, Simpson's rule was the best one, right, which gave us the exact value. Now, what we want to talk about today is we want to look at two things. Let's talk about topics for today. We wanted to look at some error analysis. And then we want to talk about the Romberg algorithm. Error analysis and then the Romberg algorithm. That's what we want to do. And if you guys remember from last time, we talked about how the composite methods, like the composite left endpoint method, had an error that was no bigger than h, b minus a, divided by 2 of f prime at z times h, right? We saw this last time. And that the composite trapezoid method or trapezoid composite method had an error that was less than or equal to b minus a divided by 12 times h squared times f double prime z times h squared. And our composite Simpson method this is the 1/3 method, had an error that was less than or equal to the absolute value of b minus a over 180 times the 4th derivative of f evaluating z times h to the 4th power. Okay. So this is what we seen last time. And just like we dealt with Taylor series and with Lagrange polynomials, it would be nice to know how many intervals do I need to split up how many subintervals should I have in my interval to get a good approximation of my interval for a function. That's what I would like to know. How many subintervals do I need to split up the interval from A to B, right? When I integrate, to get a good approximation of my definite interval using each one of these methods. So that's what we want to talk about right now. So I'm going to say this. Determine the value of n that will ensure an approximation error of less than 0.00002. Do I have enough zeros? There should be 4 zeros. When approximating. The interval from 0 to pi sine of x. When employed A, composite left endpoint. B, composite trapezoid. C, composite system. I want to determine the value of n, right? How many subintervals? How many subintervals do I have to break up the interval from 0 to pi to guarantee that my approximation of the interval has an error less than 0.0002? Okay? That's what I want to look at. And just like we dealt with before, we have these errors that we can use, right? All of these errors that we can use. And we're going to use those now. We just need to be able to grab a little bit of information. Okay. You need some information. Always useful to have. I need to know what A is. B, right? What else do I need to know? F prime, F double prime of X, and also F triple prime of X, right? Although the fourth derivative of X I need to know. Well, I guess I need to know F triple prime to know the fourth derivative. So I have A, my A should be equal to 0, right? B is equal to pi. My function is sine of x. The derivative of sine of x is cosine of x, right? Derivative of cosine of x is negative sine of x. Derivative of negative sine of x is negative cosine of x. Derivative of negative cosine of x, we're back to sine. Now, what is h? I guess I should know what that is too, because we need that. H is going to be equal to b minus a divided by n. So I have pi over n is h. Okay, I think we have all that we need to be able to solve this problem. We have 3 parts that we need to do. So for the first one, I really need that b minus a over 2 f prime of z times h has to be less than 0.00002. 2 times 10 to the negative 4. Actually, what did I write? 2 times 10 to the negative 5, actually. There we go. That makes my life a little bit easier. We have our pieces. Remember that I need to choose my derivative value so that z maximizes. So I need to choose my value z so that it maximizes my derivative. And of course, we know that the absolute value of cosine of x, which is the derivative of f, has to be less than or equal to 1. Right? So I'm just gonna plug 1 in there. B minus a is pi, so I get pi divided by 2. This becomes 1 times h, which is pi over n. We want this to be less than 2 times 10 to the negative 5. Really, I could take this outside of the parentheses, right? Because all of this is positive. So I just need to solve this. When it's pi squared, this is for the left equation. So I have pi squared divided by 2n is less than 2 times 10 to the negative 5. And then I just solve for n. This one you can actually just plug into your calculator and it'll tell you what the answer is. This is nice. So if you do solve this into your calculator, it'll tell you what the answer is without giving you any trouble. When I did it, I got n is greater than or equal to, has to be greater than or equal to. If I did it correctly, I have 246,787. So I need to split it up into 246,787 subintervals to guarantee that my approximation error is less than 2 times 10 to the negative 5. What about B? Next one. I want to use the trapezoid rule, right, for this one. Plug it in, plug it in. It acts very much the same way, right? I have B minus A over 12 F double prime evaluated Z times H squared. I want that to be less than 2 times 10 to the negative 5. My second derivative is negative sign, but that's still quite nice. We know that has to be less than or equal to 1 on the interval from 0 to pi. And we just plug in like we did the last one. So we get pi 12, this is 1 times pi over n squared, less than 2 times 10 to the negative 5. So I get pi, what's that, pi cubed over 12 n squared. And when I did this one, I was also able to solve this in my calculator. Solve for n. And when I did this one, I got n has to be greater than or equal to 360. That is a lot less subintervals, I have to tell you. That's like night and day. I mean, this is a huge difference. And last but not least is C. Composite Simpson rule. Here's my error for composite Simpson rule, B minus A over 180 times the fourth derivative. B minus A over 180 times the fourth derivative, evaluate Z times H to the fourth. Whether it would be less than 2 times 10 to the negative 5. So if I plug in, I get what's that? Pi over 180. Fourth derivative of f is sine of x. Sine of x is less than or equal to 1 on the interval from 0 to pi. H to the fourth, so I get pi divided by n raised to the fourth. I want that to be less than 2 times 10 to the negative 5. And if I do that one, if I calculate that, use my calculator, solve for n, I have n is greater than or equal to 18. That's what I need. So pretty neat, right? Simpson rule only needs you to break it up into 18 subintervals. Remember, for Simpson rule, you should always use n to be an even number, right? So for Simpson rule, you should not use 17 subintervals or 21. You need to use either 18 or 22 or 20, right? Whichever one is closest. to your number, and you want to make sure that you go over to guarantee your error is met. All right, so that's kind of the error analysis I wanted to do with that, and then I'm going to talk about Romberg's algorithm, and then we're going to finish up with this particular section, and we'll talk about Gaussian quadrature next time. So I'm going to erase this. And we're going to keep Romberg algorithm fairly simple, fairly straightforward. I know that the book goes into quite a bit of detail about it, and it does it a little bit differently from what I do, but you get the same thing. So if you want to do the book's way of doing it, that's perfectly fine. However, I like the way I have it because it ties it back together with something we've already talked about. So here we go. Let's talk about Romberg's algorithm. And Romberg's algorithm uses composite trapezoid. And Richardson's extrapolation. To approximate definite intervals. It uses composite trapezoid rule and Richardson's extrapolation to approximate definite intervals. Remember, I told you guys that Richardson's extrapolation could be used for other formulas, for other derivatives, and for other things as well. And it can. We can use Richardson's extrapolation, the idea of it, to actually help us to approximate an integral better when we don't have a small step size. We don't have a small h. We just have maybe our h can only go to maybe 0.25 or 0.4 or something like that. So we can't make h too small, but we still want to get a pretty good approximation of the definite interval. So this notation is going to be different from what the book has, but it's going to do the same thing. Because I want to tie it together again with Richardson's extrapolation. So here it is. I have R sub 1h is going to be the composite trapezoid. For on the interval A to B using h for the length of subintervals. Okay. And initially we have h is initially h equal b minus a, which is the distance between a and b. So initially for the first one, for also 1h, the first one that we do is my initial value, my initial h is going to be b minus a, and then remember we're going to half it each time, just like we did with Richardson's extrapolation. R sub 2h is equal to R sub 1, h divided by 2, plus 1/3 R sub 1, h divided by 2, minus R sub 1, h. R sub 3h is equal to R sub 2, h divided by 2, plus 1/15, right? R sub 2, h divided by 2, minus R sub 2, h. And if you guys remember from last time, R sub k plus 1, R sub k plus 1, h. is equal to R sub k times h divided by 2 plus 1 divided by 4 to the k minus 1 R sub k h divided by 2 minus R sub k h. And this is for k greater than or equal to 1. Right, so this is the general formula, is the one that I wrote at the very bottom of the screen. We have R sub k plus 1h equals R sub k, h divided by 2, plus 1 divided by 4 to the k minus 1, that's in the denominator, of times the quantity R sub k, h divided by 2, minus R sub k, h. And this is for k greater than or equal to 1. Okay. So, like I said before, this looks a little bit different from the way the book has it, but I wanted to tie it so that it looks just like that Richardson extrapolation that we did, because it is essentially the same thing. But instead of differentiating, we're integrating. Let's look at an example. Here it is. Approximate the integral from 0 to 2 of x cubed dx using the Rumberg algorithm approximate up to R sub 3h. And use 4 decimal places. Use 4 decimal places. All right. So I don't know if you guys remember or not, but that was a tabular form for the Richardson extrapolation. So I want to bring that back for a Rumberg algorithm. I have k, value for k. I have big O of h squared. Since I'm going out to 3, I'm going to have 3 columns. Big O of h to the 4th, and then big O of h to the 6th. I'm going to leave some space. I have 0, 1, 2. And if you guys remember what I told you before, when we talked about Richardson's extrapolation, I want to do the first column first. So I have R sub 1h, R sub 1h divided by 2, R sub 1h divided by 4. Then we will have R sub 2h, R sub 2h divided by 2. And then our last row, the last column will be just R sub 3h. Okay. And so let's fill it out here, right? So that's kind of the form of this guy. 0, 1, 2. Okay, let's put some numbers in there. We need to calculate R sub 1h, R sub 1 h divided by 2, R sub 1 h divided by 4. It would be nice to know what in the world is h, right? What in the world is h? H is going to be equal to 2 minus 0, which is 2. Okay. So that's going to be my h that I use, 2. Let's look at R sub 1, evaluated at 2. Erase some. Let's do it over here. Remember that the R sub 1 terms are going to be our composite trapezoid rules. So R sub 2 is my h. Right, remember the trapezoid rule is going to be h divided by 2, so I have 2 divided by 2. Okay. I'm not splitting this up at all, right, because we're going over the entire interval, right, for the first one. So we get f of 0 plus f2. So I get 1 times 0 plus 8, so I get 8. So that goes right here. R sub 1, now I'll do h divided by 2, so that's going to be 1 here. So I do the trapezoid rule where I have my h equal to 1. My interval is still from 0 to 2, right? So I have to split this up into 2 pieces, right? So my h is 1, so I have 1 divided by 2. So right, this goes right here. This is the value, this is the length of my interval that I use now, 1. So it's 1 divided by 2. This becomes f of 0 plus 2f of 1, right? Plus f of 2. Let's compile the trapezoid rule. So I get 1/2 times 0 plus 2 times 1 plus 8. And that gives me 5. And that goes right here. R sub 1, I need to divide again by 2, I get 0.5. So 0.5 divided by 2. And I split this up again. Now I split it up into 4 pieces, right? 4 pieces. So I have f of 0 plus 2 times f of 0.5 plus 2 times f of 1 plus 2 times f of 1.5 plus f of 2. So what did I get when I do that? When you plug all that in, I'll just tell you, you get 4.25. So 4.25. I'll put it right here. .25. Right now that we have the first column done, we can use those values that we have to compute the second and the third, right? So R sub 2 of 2, right? R sub 2 of 2. You guys keep a track, right? This is going to be my h, right? It's going to be equal to, looking at this, that's going to be R sub 1 of 1 plus 1/3 R sub 1 of 1 plus R sub 1 minus R sub 1 of 2. Okay. Let's plug in R sub 1 of 1, so that's going to be 8, so it's going to be 5, sorry, plus 1/3 8 minus, sorry, 1/3 of the quantity 5 minus 8, sorry. So it's going to be 5 plus 1/3 times the quantity 5 minus 8. And that gives me 4. I do the same thing for the next one. R sub 2 of That's going to be r sub. If we're keeping track, r sub 0.5 plus 1/3 r sub 1 of 0.5 minus r sub 1 of 1. So that's going to be 4.25 plus 1/3 of the quantity, 4.25, minus 5. And you know what I got? I got 4. Huh. 4 it is. Now notice that these approximations should be better than the approximations we had in the first column. And what about my last one, r sub 3h, right? I'll erase this one. I don't need it anymore. R sub 3h, which is 2 in this case, is equal to r sub 1. R sub 2, sorry. 1 plus 1 over 15 times the quantity, r sub 2 of 1 minus r sub 2 of 2. Plug that in. Be 4 plus 1 over 15 times the quantity, 4 minus 4. I think 4 is the answer. 4. So we get that r sub 3h, this is my best approximation right here. So I can say that the interval from 0 to x cubed dx is approximately equal to 4. Now, that's what I think. What is the answer to this, right? Let's integrate this. One-fourth x to the 4th, 0 to 2. This becomes 16 divided by 4. That is 4. Well, actually, our approximation is actually the answer. Now, why does that make sense? Why does it make sense that this approximation is the answer? Well, it's probably right here. We have h to the 4th. So usually h to the 4th is going to either correspond to the 4th derivative or maybe possibly even the 5th derivative. Whatever the situation may be, the 4th derivative of x cubed is going to be 0. So at this place, we have no error, right, at this location. And we're good to go. So there's our answer. And that's Romberg's algorithm. And that's all I'm going to do over there. I'm going to give you guys maybe a one homework assignment about it so you can see how this is very similar to Richardson's extrapolation. Right. So that's it for today.